Welcome to the second part for our lecture on the basics of singly linked lists, kind of your first step into making linked lists and then trying to make variations of linked lists. So before we went through a bunch of methods for adding to a linked list, doing some quick variations, and things like the add middle due to the design of the function was a little bit more complex, but it brought to light the idea that you have to worry about special cases and what is going on. So we're going to continue on with adding new methods to this actual class, and then as we add them, we'll see if we can start improving our design of the previous methods to kind of make the code a little bit better as we go. So next, we've got to add in a method for retrieving an actual element. We have done so far adding to the list, but it's kind of pointless to add stuff to the list if you can't then get it back out of the list itself. So we're going to go and basically make the equivalent of the actual get method from the ArrayList class, but now in our linked list, that you give it an index and it'll return the data from that index. But we've got a bunch of special cases to deal with once again, that you have to worry about if the list is empty. You have to worry about if they give you an index that's out of bounds, so it's less than the size of your list, so a negative number, or it's greater than the number of nodes that are currently in your linked list from there. And then we have to move our proper moving reference all the way up to that point and get the actual data. So for this method, we've actually kind of done some of it already. Like that we know, like here we have to go we need to check for an empty list. We need to be moving a reference to set up and move it forwards until we reach a certain spot. Well, we had that with the add at location with index, where it had to move a pointer up. So we have the first step in our class design here that, well, we have a common feature that both of them use, which is getting a reference up to the current node at a spot that we want to do work around. So with this, let's step away from the slides again and go back to the actual code. So again, before we finished, we last finished off with the add at method with the actual index. Next, we're going in and we are completing the actual get index method. So given an index gives back the data at that one, or it will throw exceptions to deal with if it can't find it. So we have some beginning cases to start with to worry about. So if they give us an index value that is less than 0, so it's a negative number, we should indicate an error. And also, if they give us asking any index value 0 upwards if the list is empty, we need to indicate if there's an error. So here we'll do that again because we're returning data here, so we can't return an error code. We don't know anything about that, so we have to use exceptions. And so for the purpose of this course, we'll just literally just throw the exception class. There's a ton of other exceptions that are out there. So first thing is to check setter conditions before we throw. So if the index is less than 0, being that it's negative, or if the list is empty, now we can just go throw new . Right here. So again, if index is less than 0, or if the list is empty and they're trying to retrieve something, you just want to throw index out of bounds. That the value they've given doesn't work because either there's nothing there or they've given a negative value. Past this then, we want to start moving through, like setting a moving reference again to the start of the list and move it forwards until we reach the desired index, or if we hit the end of the list, indicate an error. Now we know from above that we already did that. That's what this step did right here before we went on. So I'm going to copy this for now, but we're going to see, can we start making this generic? We'll get the get method working, but instead of just having this same code copied and pasted, I'm going to come back and modify both these methods to create a helper method once I've got it done. Where we can, instead of having duplicate code, we can create an internal helper method to do the work that then both call. So here, again, to get started from the beginning, since I can't randomly index in, is that we're starting a reference at the beginning of the actual list. And then we are stepping forwards until we've actually moved it the same number of steps as we need for indexes. So assuming that the first node in the list will be index 0, then index 1, then index 2, then index 3. So we first move it forwards to the next one. So the your moving reference equals to its next reference from the current node it's at. If after doing this we find that m is equal to null, it means we've gone off the end of the list, and it means they've given an index value that does not work at all. Because if they've asked for index 5 and we only had 3 nodes, which is 0, 1, 2, well, they were expecting 6 nodes, and that's way out the list. So we've moved forwards, we've gone off the end of the list, we can't move anywhere yet, and we haven't ended from right there. So before we're going to step, so no, like this can't. We've moved off the edge of the list, so we should throw an exception. Hey, you've given an index out of bounds. You need to deal with this coder who has called this method. After this, what you assume is, again, since we've checked if the index is less than 0, we've checked if it's empty. We've then moved it forwards, and if it's gotten all the way down here, we've moved the correct number of steps and we haven't gone off the end of the list. So m now should be at the proper node to get the data from. So we just need to access that node and get the data out and then return it. It's as simple as that. So a very similar step to what we previously saw. What we need to worry about now is, yeah, we've got this done. Sure, it's not very tested. Maybe there's a few bugs and we've got to test this a little bit. But we've also got to see, like, how can we fix up the class? Like, I just copied and pasted some code, and, well, that's not good design. Like, we shouldn't have to just copy and paste and have the same code here, because what if there was a bug in this and, oh, I've duplicated it here? We might as well instead is extract a method and make a helper method that both of them call, and that maybe will be useful in the future to get work done. And what I see commonly here is having this where given an index, it moves a moving reference forwards. So this one is just getting the data. This one up here is doing work with it afterwards. So maybe I can make a helper get method that returns the node at that index instead of just the data, and then allows the other ones to do its work. I'm going to make this private because I still don't see a point to having anyone outside the linked list class have to work with nodes. It's all handled internally. They should be just trying to use a list type feature. So I will make this private. I will say it will return back one of our generic nodes, get an index, give the index of the node a return. And we're still going to have to deal with the bounds checking for right now. So I will have it throwing exceptions. Now this becomes even smaller here, is that it is generally just this same code that we had before. So I move it up here. And the idea is this is checking if that index is within bounds. Otherwise, it'll throw an exception. Boom. Right here, we then start the node at the actual beginning. We step it forwards. If it goes to null, we throw an exception because we've gone past and it's a wrong index that's given. And then otherwise here at the end, then instead of return the data, we can just return the current address where the moving reference is actually at. And now here, just to fix this small error, I got to give this a different name. And it's called get. This is called get node, just because it was causing issue with this one down here. So again, this one will probably give it an index. We'll deal with bounds checking. We'll take a moving reference and move it forwards to the right location. And as long as we get down to this return statement here, this will be a reference to the node at that specific index, saying that we start at the first node as index 0 and moving up from there. So now we can come back and modify this method to be a whole lot smaller, because we don't need now to do our duplicating our code of moving a reference forward. We can just call our getNode method, passing in the same index. So from here, what happens, again, seems weird for the exception system. If an exception is thrown from here, when we come back to this method, all code will stop. We won't go on to here. The exception will then also be rethrown because we have this statement here, and it will continue up the chain. So error checking is still done. And so if we get to this line, it means everything was still right and we can access and return the data. And now with the same helper method here of this get node, you can pause it if you didn't get everything from there. I was moving too fast, so pause the video right now and copy down this same code for the get node method. I can now go up and I can shorten how much code we have, because right here, all of this code is the exact same thing for getting the node. Passing in the index that we were given, so making sure this works. So we have the index, we have all the rest of the code that we need. We have this where it moves it forwards. If there's any exceptions, it'll stop here and leave the actual method. It won't continue on. So again, once we get here, we'll do everything in dealing with our checks if we're at the end or not. So now we've cleaned up the code a little bit. We've made this a little bit smaller. And we have this reusable thing. If we ever need to get a node by an index, we have this method. And we made the get method a whole lot smaller from right here. So just reusing the code to do some of the stuff. And you can see where this is kind of leading to is that we also then have this remove at method, which later on will help us giving an index, is that we can also use that get node there as well to do some work, or we'll see if we have to modify something else because we have to move through the entire list. So we will try our best. Okay. So let's switch back to the slides for a second and then step on to the next method to code. So that was retrieving this. Next, let's work on how we can do the size of the list. Being like, how can we easily keep track of the number of elements or nodes in the actual list? So just like you had for the array list that you could tell its size, the amount of data, it'd be nice that we could see how many things are currently within here. Right now, this is just as method just returns -1, so this compiles, but we've got to update this. And we've got a couple ways that we could go about this. One way to solve it is just to count the number of nodes. From here, that we may not know what's there, but we have the start. We know that we can move through all of the actual nodes, and we know that we can count every time we see one until we reach to null. So let's start doing that one, but I'm going to say there's a better way to do this that's more efficient, but I want to bring in again that you can have different algorithms for the same problem, that time complexity stuff. So let's start here. So with the size, we can have int count equals to 0 to count how many nodes we've seen so far. I will just automatically return this count. Right here, and then now what we need to do is again start moving through the list. So always starting with that, we can go checking first if the list is not empty. So going not is empty, we can go in and do the count. If it is empty, the size is 0 and that will be returned. Set up our moving reference. The beginning of the list. And we will go while m does not equal null. So we will let it run off the end of the list. We're not checking the m.getNext to see if the next thing in front of us is going to null. We just want to let it step off the actual list. And we just keep moving forward. So m equals m.getNext. And then every time we move forwards once, we will just increment our count by 1. Count plus plus. And so the idea that this will keep going through, so starting at the start, and as long as this isn't null, we'll go in and say move forwards 1 and count 1. And so move forwards, count 1, move forwards, count 1 until finally this is null. So we've got, after this, we've counted the last node, we've moved off the edge of the list, and we've left and we've come back here. So this will basically work for the side. This is basically like counting each one by one. But an issue with this method is we start looking at it for complexity as a way to solve this, is that every time size is called, it's going to take n steps to actually go through. Being like this is a list. If there's 1,000 nodes in the linked list and we call size, then it's going to take It has to go through that loop 1,000 times. You have all the consistent time for here. You have this, which is repeating for 1,000 actual times and going forwards. And so if this is the size of 1,000,000, or even if it's just the size of 100, but we call the size method in a whole lot of places in the program, this is going to take a lot of time to keep going through. And so this isn't the most efficient way to actually keep track of the count. And this is just a way that if you're given a list and you don't know the size, you can find it out. But we're inside the class that's building this. We have access to all the methods, and so we could have a way that we keep track of a tally as we're adding or removing. So as long as we add that ability in, we could make actually this size method a whole lot faster. So I'm going to delete this for right now. And what we can really do is just basically as we add and remove nodes, we can actually just update a count. And so instead of taking n every time for the size, we just have this like little constant time when we update and add or remove of adding a number to it or removing it, and then getting the size then becomes a constant time. So since it's going to be for the lifetime of the list, I will set a variable where we can use to keep track of it. I will set it to 0 in the very beginning, right here, that there's nothing being added to it. And now I'll go through every method that where there's adding or removing, I will update this list size when it properly happens. So first, here the add to start. We know we have the node, and we know if it goes in here it's going to add, or if it goes in here into the else it's going to add. And so we can do in the bottom of this method, we can just increment a counter, because no matter what, if it goes into the if, it's going to add one node. If it goes into the else, it's going to add one node. And so we go through the if add, it's going to go down here. Otherwise it goes into the else and it comes down here, and we're adding one node. And we know there's no way of leaving this method where it's not going to at least add one node to the list. So I will just have it increment, keeping track of, oh, boom, I've added one to the node. Same thing here for the end. That we know, okay, if it's going to come into here, it's going to add one node, or if it goes into else, it's going to go to the end of the list and add one node. So we can then go this size plus plus, increment it from here. And then finally at the add at, we can go through deciding, okay, where's the best place to do this? So the add's going to come in here. If it goes into the add start, that's going to add one to it. Else, because we know the add start, we just did it in there. If it adds it to any time, it's going to add it in there. Now next, if we have right here, this is the code where it's going to move it forwards and add it to the middle or at the end. So here, checking the bounds, checking. Here, if we're adding to the end, it's going to add. Else, it's going to come here and add. And so right down here, before I go further with the brackets, as I know this bracket that's right here goes up to this else, is that, okay, I know if it comes in here, either it's going to add here or it's going to add here. So I can go list size plus plus. Now I'm making sure not to do it at the very bottom of this method because I don't want to get my size done wrong, is that I know in my add start, we're calling it there, and I already have it incrementing the size. So if it's going to go into here, I don't want it to come back as it would and go down here and then have the list size plus plus. Then you'll have, every time you add a node that way, you're going to get this count wrong. And so I'm just making sure, okay, it's handled there, but within this code where we have more adds, it's not handled within here. So I've got it done right here. But what I have to worry about is, okay, well, where else does it update it? The get node, that doesn't add any nodes, just retrieves ones there. Your get, that returns the data, that just retrieves the data that's here. This find, that's just going to return the data, not remove it, but this remove is going to have to deal with that. So I'm just going to make a comment so I don't forget right now, is that when we come in here, we have to make sure to update the list size. So after we deal with the remove, we're going to have to deal with the updating of the list size. So when we come down here for a size method, then it becomes even smaller. Instead of that, again, while loop that's increasing forever, that if we call it a whole bunch, it's going to slow down another program that's calling the size, and it's taking n, and in the order n family, so for big O, we can just go return list size. And now we've turned this method, instead of taking a growth function of basically n, this takes constant time of 1. And all we had to do to that was add a little bit of extra time that's being taken in the add methods we've seen before, the remove to the update, but that's a very marginal change that's being added from here just to update to make this method go faster. Okay, so we've got our size. What's also now is nice is before we go on is some of the methods when we designed them earlier on, like that get node and checking for the index and everything else, was based upon the size. And so say if we went off the edge of the list or anything else. So now we could actually make another helper method to deal with the checking the bounds of an index. Right now that we have this size method here and we have a way that we're going to be updating the size, and we can go hopefully fix up the rest of their code. So I'm going to now create a new helper method then that will be used. I'm going to code it down here at the bottom just for arbitrary reasons because we just did the size, but it'll be used to validate the actual index, and it'll use the actual size and then shrink the amount of code we need to have for where the exceptions happen. So I mean by shrink is how much of the error checking code where we check for the error and then throw an exception. So what this is going to do is check index. Is that if this method cannot type right today. So this message will validate the actual input that you're working on, and if it returns, it means that the index is within range, but if the index is not within range, it's going to throw an exception. So what we can do is, okay, if index is less than 0, so it's negative, or index is greater than or equal to our size, so the number of nodes we currently have in the list, then throw an exception. Now we have this one. So again, if it comes in here, if the index is out of bounds, it throws an exception, kicking in the exception handling system, which will propagate everything up till someone handles it with a proper try catch from here. And if the index is proper, it'll just leave this method and continue past there. So now we can go up to every place we've had error checking so far for the indexes. So you can see, oh yeah, and I almost forgot something right here. So if it's less than 0 here, or is empty. I'm just being paranoid. I just noticed it here as if the list is empty. So even if we've got less than 0, if they give us back 0, there should be nothing that's in there. And then we have, if the list is actually empty, then also have it. So I was just noticing when I went up that I almost missed something due to error checking there. But just again, if the index is out of bounds or the list is empty and they've given any index value, then just throw an exception. So now we will go back up and modify everything we had. And I just noticed because of here. So first off, we can just have checking our index. So take this out. Right here. And again, the idea is that if there's anything wrong with that index, so being an empty list or any index values you have, the exception will be thrown from here. None of this code below will be run and will exit out of the actual method. This line we do not need here anymore because if they've given index value that's bigger than the number of nodes, we will never reach this line of code, so we can just make this a little bit smaller. Right here. So we can see how we've shrunk this down. All the error checking is here, so if we get past this line, we don't have to worry as much as like having nodes that'll go out of bounds for the index because we've already checked and validated the proper size. So let's go up and see if we can actually make a little bit more of the rest of the code a little bit smaller. So we had this add right here. So now we can add the check here. So if we add the check and an index is within bounds, we'll get past here. So this first if we don't need because we know we've already made sure that the indexes are proper. So take out that exception handling right there. check the rest of the code. Okay, if index is equal to 0. Okay, that is fine. So the list is not empty. Oh, I just realized a small error. Isn't this love? Coding stuff fine. It's just if the list is empty and we're trying to add at and the index is actually 0 from this. Okay. Well, I'll keep going on. We'll come back to that one. I'll mention what I just noticed. Okay, so if index is equal to 0, we're adding to the actual start from right now. Here we'll go through here. Is that we shouldn't have to deal with this right now if the list is empty, but getting index is fine. This will validate and throw any errors as well. Do the add. So if we're at the end of the list, I'm just going to take these brackets out to shorten the code some now. Okay. Making sure everything lines up with what we need. Okay, so far this is fine. I just want to check and make sure I haven't added something weirdly in. So for add at and their index 0, this method was then going to allow that. It could add it because we want to add it as the very first element that's in the actual list. So I'm just going to change the way that this function. Nope, I should think about this properly. Okay, so thinking about this should be okay because this add at was supposed to add after the current node. So this should still be okay. So they give us index 0 and the list is empty. We should just leave because we can't add after it. There's nothing actually at the actual list itself. So we should be okay for the way that this one was designed. That it's just taking this index and it's adding the node after. The new node comes after that spot. So if there's nothing in the list, we can't do that at all. So I'll leave this check in. So this add at, depending on how you're implementing other times, maybe you need to change it, but this will just be if the list is empty or the index out of bounds, you can't use the add at for right here. So we should be perfectly okay for the rest of this moving forwards, and everything should be shrunk down. So a little bit of shrinking the code down now based upon doing this check index. So after this, we need to move to the next steps of searching through a list. So retrieving a list based upon, so we've done the size, we've implemented the size, then shrunk our code down to make it work with the current design of the actual class that we're working with. We have this remove element, which is larger, but I'm going to skip just for this video purposes right now. Instead of going to remove, because the larger thing to do is I want to go on to the actual searching of the element right here. Now when searching for an element and we're working with generics in Java, we need to go back to having some way to compare the actual data. And just for this course, I just want you guys to use a comparator as designed, that you can be given a comparator to compare two objects between itself. I know we've seen it before, is that this interface can be set up, it's within there, it'd be generics, and it takes two objects and it returns a negative number if this O1 is less than O2, returns back 0 if they're the O1 equals O2, and returns back a positive number if O1 is larger than O2. So it can be used for sorting and everything else. We're just going to be looking to see if we can find some data, and the comparator that the actual user of the linked list class provides will tell us how to tell if there is an actual match. We just need to know that we can call this method and return back 0 if there is a proper match, and that other method that's passed in will do the proper comparison of two objects for us. And we don't really care at this point in time. We're in here. So for this find, we will now go through the same thing we've done before, is that we want to be able to return the data in the end. But we have to step through the list one by one and then actually find that piece of data to return. So anything in the list or searcher, we need to go through every element one by one, and we can start at the beginning. So we can set up our moving reference again. And we can move till we get to the end of the list. Now what I'm doing here is I'm going to allow the moving reference to go off the list. Because if I went m.getNext like that, remember that we're comparing the current node we're looking at, what does it next point to? And so that's where we're trying to stop where we have a reference at the end of the list. But if we want to go through every single element, the list, and checking all of them, we want to let it go off the end of the list so that we're checking the first one. If we didn't do that, we'd be missing the very last node in the list. So things like this, get next, would mean that we're not looking at the data in the next node, we're seeing if there's another link in this current one. So if that is the case before we went and do any work, is we'd stop and we wouldn't check what's in that last node itself. So we want to go all the way to the end, which could happen because what if right now that what you're searching for isn't even in the list? You have to return back that there is nothing. So right now what we would do is first we get the actual data out from the object, and we have the data that we want to actually compare to. So we can say type current node data, go with a really long descriptive name, equals your m.getData, so get that out. Then we can start comparing the data. So we get our CMP, our comparator dot compare, and we have to compare the two. So we have the data being the one that was passed in that we want to match to. We have the actual current node we're looking at, and if that is equal to 0, then we found a match and we can stop from right here. I'm going to use the break command, because what this means is if we found an actual match, it means M is at the current node with the correct data, so we can stop, and we can leave to exit out of here. Now, while there's two cases of what could happen is that if the list is empty, start will be null. So this M will be null, and this won't even go into the while loop, and we'll have null down here. We can come in here and it's gone through every single element, and it's gone off the last node and hasn't found a match, so M will be null that we found right here. So basically we can realize if your moving reference is null, that means, well, okay, we've either gone through the entire list and not found a match, or the list is empty, so there is no match. So when there's no match, and so if M is not null when we get down here, then we do have the actual right data. So if we go if M is equal to null, well then we don't have we don't have the correct data, hasn't found, and so we can just return back null, indicating that there was nothing that was actually found at that spot. Otherwise, M will be actually at a node, and we can get the data out of it and just return that. So again, M equals start. If the list is empty and starts null, it will not go into here, skip over the while loop, come down here, M equals null, and it'll just return back null, that there was nothing found at that spot. So there's no match that's found, and we see not null is the match. Next, if we come in here and we go through the entire loop itself and there's no match that's found from right here, then M would have gone off the end of the list, which would have made this null. We would exit this while loop, come down here, go into the if, and then it will return null right there. And then finally, if it comes through here and the list is not empty, and we've gone through and we have found one match right here, then it will then break, come down here, M should not be null because it's still within the list, so it'll go down to else, and we can get the data out of that one. So there we go. You got your find, you've got your match, you've got the calling the comparator that you're given right here just to check, passing in the actual data, and if it returns 0, then we know that we have a match. Okay, not too bad so far, but we've got a larger, a little bit more complex one to deal with. And that is the remove of this code. So why I just wanted to jump ahead to doing the actual matching. So now an issue with remove is there's a bunch of special cases just like the add. So we have a remove at, in this case, so it's giving an index. So we have to worry about, okay, is this index within bounds or everything else? So if it isn't, we need to just exit out. from there, but we have a thing that can help us with that. But we also have to worry about, okay, if the list is empty, so we can deal with that. Removing from the front of the list, so what if the index they give is the actual start of the list? So we need to worry about that. We then need to worry about what if this is the end of the list itself in a special case, because there's a different way to have to remove that. And then we need to worry about removing from the actual middle of the actual list between the nodes. So how do we update the all the actual references based upon what we're seeing? So first off, we'll come in and we'll just deal with this list is empty. That we already have something to deal with that. So we got right here, we got to remember that we need to update the list size properly as we're dealing with this and returning the data if we find. So what we have to do for is if they give an index or the list is actually empty, we already have our handy dandy check index method that will throw an exception. So we need to add in throws exception right there. So that deals with the emptying the list. The next is we actually have to move the actual, getting a moving reference to the right location to do our work with. But one problem we have is going to be, okay, well, we need to move stuff forwards, but we're going to have to worry about those special cases for removing, say again, is at the start, end, middle. So we may need to modify code that we're using, but we'll try to work with what we have so far. So we know so far we have a moving reference, something that'll get us the actual node, and hopefully that'll be enough for us to do our work with. So, well, okay, how about we just get the node that we actually need to delete first, and then worrying about deleting it properly. So we can then, okay, type. I don't know why I can't type properly today. Okay, node to remove equals get node, and we can call our get node method we made before and just get access to that. So this would have done all the validation. This should give us back a reference to the actual node that we actually need to remove, and then we can start comparing and doing our work for the conditions we're at. So first, if we're at the start, and so you have to realize if the node we're removing is the start, we need to check for that. And we can just see first off, okay, well, what's the address? Because the start reference, the node here, if our to remove, and we got the reference to it, it should have the exact same memory address as the start reference. Right there. If that's equal to start, boom, then we know we're at the beginning. That's the idea. We have two references. So this is search through. We've given it the actual index. We not know anything about it, but now if the start reference is pointing to the same thing we have to remove, it means we're trying to remove the very first node in the actual list itself. Else, we have other work, but we're going to deal with this first and then come back. I want to jump then now, instead of jumping straight to the code, we can draw out a kind of visualization of what we're seeing here. So what would happen is we have a couple cases. We could have this case right here, that we have one node right here that's null. This is at index 0. So they have done a remove at index 0 that they're trying to do. We have validated that everything's right by the size of the index. We would have gotten this, and we would have gotten our to remove reference, which would be pointing to that right now, because if we gave it index 0 right here, should give us back this reference. And we can see that, yes, we can see like, okay, here and here, those are both referencing the same object. They're pointing to right here, so yes, we would go into the actual checking of this. So what we've got to worry about in this case is, okay, how do we start moving everything first? That we're removing the node, but this has got to move to everything else afterwards, and we got to keep this for the actual data itself. So in this case where we just have a null and there's only one thing in the list, what we could start by is, well, we could make start equal to the next node that's right here, because that'll be null and then there'll be nothing that's in the actual list. So we could have your start equals start dot get next, like that, and move it forwards, which would set it to null, which is okay. We have the to remove that we can get data out from it, and then we just have to make sure to update our size that we're keeping track with, that we increment it, that it goes down. Now another case that we could have, we want to see, is if we have more than one node in the actual list. So if I have, again, start, right here I have one node here. This is referencing it. That references off to, say, another node, and even to make this longer, goes off to another node before it goes to null. So index 0, index 1, index 2. We then said we wanted to remove on index 0. Right here, our first code for getting and moving the node to getting the node for that index would give us a reference to this one right here. Now after this, we would want to make sure that, okay, start has to reference over to here properly. And then we would also then want to make sure that this node is not linked in, so this goes down to null right here, because we don't want any references on. We want to make sure that everything gets removed. So if I bring that all back to where we were before, we would want to move the start first over to here, because if we change this to being null, so if we change this reference to null here, we would have lost the links here. So we need to move start first, and then we need to unlink this entire object from here. So step 1, start has to reference now over to here. So we can do that by getting reference to what this one is, and then setting start equal to that. And then next we can then take the to remove and go up and set this one to null. So we've removed the node properly, and then we can get the data out of it and remove it from there. Okay, to deal with this now, let's jump back to the code and start implementing that. So first off, we need to move the start reference. So we can just advance start forwards. Start equals start.get next. So this is perfectly valid to do because it always goes from this right to left. So this will be executed first before we change it. So start.getNext gets the reference of the object afterwards. So that means from this chart here is that we're going from start, going to the next node that's over here, and then getting the reference to that object and setting it. So we've moved that forwards. We then want to make sure no matter what that our to remove dot set next is not linked into anything yet because we are removing it from the list. So if this was the last node, we're just setting it back to null again. If it's not the last node, then it means this node is not linked into the list. The start is moved forward first. We have then done this, and then we next just have to be careful then to update our list size to decrement it to make sure that everything is working properly. Okay, so that should work for this one. The next case we have to worry about is, what if this node is at the end of the list? Now, we need to do another check here. And you have to remember, if we're at the end of the list, then that just means that our to remove node is that its next is null. Because remember, the end of the list is always marked with null. So to remove dot get next, so kind of do a probe to see what's coming after this. If that's equal to null, then it means we're in the middle list. So the first one, if start remove is equal to, if to remove is equal to start, then we're at the beginning of the list. To remove dot get next is equal to null. So if it's not the start, it means this must be an ending node. right here, and then we can start doing the remove. Now we're going to see is hopefully we have all the references we need, because we only have one so far, but we have to see, do we have all the references we properly need to get the work done? So let's go back to our drawing and go through the couple situations we could expect to see. There, I'll just scroll down and we'll start on a new. So we could have one case of list being empty. That's fine. We've dealt with that above, that check index. We wouldn't even be coming in here. Next, we could have start with one node. Right here. And so then when we did remove and it's the actual end, so we got index 0, we wouldn't even have this case hitting here because we know so far if end and start are matching, if we go back, we know, okay, well the to remove would have found is index 1, so the to remove, index 0. We're referencing here, so start equals to remove, and so then in our code we would have already been handled by this case, so we don't need to worry about the case where this is remove and we are removing the first start node. That's handled already above here. So we'd be dealing with more where there's multiple nodes in the actual list and we're removing the very last one. So I'd have, say, another node here, then another node here, index 1, index 2, and we'll say that this is the node that we want to remove. So we would have a reference to remove, which would be referencing up to here. Now we know we've got to remove. We can see that, oh yeah, it's got .getNext as null, so we are the end of the list. But the steps we need to deal with is, well, we've got this as null, but this previous node that came here has to actually be updated to not be linking to it. But so far, all we've got for references is this one right here, and then we've got this one right here. We don't have a reference to this one right here. Like, we don't. Like, well, and we need to deal with, like, how can we do that? How can we have a reference to the previous one? So in a singly linked list, if we had this node, if it was a doubly linked list, we could access the previous and we're done. But in this case, we're dealing with a singly linked list. We've moved all the way to this point right here, and we don't have access to the previous one. And it'd be really nice if we could also have a reference to this one beforehand so that we can unlink it from the list and then deal with our work. So what we can do back is I'm just going to show you guys a trick of how you can have what's called a trailing moving reference, that it just basically keeps track of what was the previous step of where we are at. So we have our get node that we did here before, but this current get node is not going to work for us anymore based upon that index. We are going to have to set something up different. So we're going to have to modify that original code that we had. I'm going to go up and save a little bit of time. And we've got everything from right here. So this, as long as we have everything correct in our check index, if that's correct, then our indexes here should be fine, and we'll have our moving references moving forwards. But what you can do is we just need to always keep a track to where was the previous step before us that we were. And so what you can do is just literally save it. We can just go node, type, so right here. We can just say last node equals null, and then right here is that before we move to the next node, like this one's going to do here, we then just say last node equals to remove. And so the idea is here is this one will always be just before where we're going, and then we move forwards from right here. If we come down here and to remove is the start, we don't need it. We can do all of this work, but it's going to become important when we're here at the very end. If we go back to our list here, you can kind of see the idea of how that will actually work. I will try to speed this up as we're moving it. So we want to get to index 2. So in the beginning, what we'll have is we'll have our to remove is pointing here, and we'll have our last one is pointing to null. When we go into the code for our moving forwards, the first step right here, as long as we're not at the right index, is last equals to what to remove is, and then to remove will move one forwards next, step forwards. So first step is last will go to what remove is, and then next remove will go to the next one right here. And so what we can see is we have the last is to the previous node that's right here, and then the to remove is sitting here up at the next one. So if we go through from one more iteration, then you can see, okay, last will be now updated to here, and then to remove will jump to here and be referencing up here. We would have hit the index that we're actually looking for right here, and then what we have is that you can see is your last reference is pointing to the node that's before, and your to remove one is pointing to the node that you want to actually remove, which is then going to be super useful, because if we have to come in and do any of our removes after this, we now have a reference to the previous one. So all we have to do is your last one, set this to null if we're at the end, so it's the end of the list. This node is then separated from here. We know it's the end of the list, so the end reference is not linked to anything else we have coming, so we can just get the data out of it and then update the size, and we are done. So let's go and code that. So we've updated this. We know that this will still be at the right location because if we've moved it forwards, so if the index is equal to 0, we are good. Right here, and in our remove, we just want to go through those steps. Our last node dot set next equals null. So it's unlinking the current node it's at from the next one that's after that. We know that we're at the very end, so we just need to get the data back that we need to actually remove from right here. So we're okay. What I'm going to do down here at the bottom is that I'm just going to always make sure that to remove as a reference is reference the object that we're getting, and it'll be properly unlinked before this, so I'll just get it to return the actual data that we want coming out of that. So again, once we've updated the start, we've done the right remove, it'll come here and return the data. Once we're removing from the end, I've unlinked this last node, so it's the new end of the actual list. The end node will not be linked to the linked list anymore, and we remove the data. And now we're getting down to the final case of updating all the nodes if we're in the middle. So this means if that we're not at the start, we're not at the end, we're anywhere between that, we need to now properly then deal with linking and unlinking the nodes. So let's go back to the drawing. So let's go to the situation you have. You won't have one node. You won't have two nodes from here. So the idea is that if I only had one node in the list, that's already going to be handled for us because that's the start that we're doing the remove from. So we already handled checking if the remove references from the start. So this case is done. If we had two nodes in the list like this, we are still okay, because if we're removing this one, it's considered to be the start. If we remove this one right here, that is the end, so we would go into the end code. So our last case is dealing more where we at least have 3 nodes in the actual list, if not more. So let's say 4. And what we're going to do is, let's assume that we can index 0, index 1, index 2, index 3. Let's assume this is the one right here that we want to remove. So we have our code before for moving our last and first references to each one. So we know that our last previous node reference will be sitting there, the previous one. This is the node we want to remove. So our to remove reference would be sitting right here. And what we need to get done is that we need to completely extract this node out of here, but doing it properly to link everything else. So to get that happening is we need to make sure first off that this gets deleted and set to null, but we also then have to make sure that this link here will go to the node that's after that. So we want to be careful again here to always do this last unlinking. We don't want to lose anything else afterwards, so we want to worry about updating the nodes here. So step 1 of this would be taking this reference and getting it to be this node over here. And what we know is our remove reference.getNext is getting to that node. So we can go to a remove.getNext, and our last node, we can use that as the set method here. And then in here, we can just do our getNext to null, and we've now completely extracted this node, and all the indexes would then be updated. 1, 2 from there, and we've got what we needed. So we're good. Let's go back to the code itself. So first thing is to update the previous node to go past the current node we want to remove now. So that's why we have the previous node before where we're removing. We do .set next, and we want to pass in the to remove .get next, so the node after. So we're saying, hey, previous node now linked to the node after the one that we're removing. Currently, the current node we're trying to remove from the list is still attached to the list, so it's next pointer. So we want to completely make sure it's not linked into the list at all anymore. Right here, so we've got that removed out. So now that's all it is, those 2 lines. Now that we've got this thing that moves it forwards, keeping the trailing pointers that we're working with, is that we've come back here, we did that last .set next, and we did this get next. So that was step 1, and then we set this to null afterwards so we wouldn't lose this reference. So we still have the link structure we needed. We have this one completely removed from right here, and we are good to go. The only thing from this is we haven't error checked this code. That's going to be the next thing to come back and see, okay, how can we test to make sure that all the code we have in here is working properly? So I've done this quickly, and it's best before leaving this to go through, okay, what is happening in each method from here, and making sure, okay, is this actually properly working? But you got your basic idea, and you can see the idea of validating and making sure you got the right tests. How can you visualize the steps first and know all the special cases of what could be happening, and then implement that in code, and as you work stuff out, going back and cleaning up your code to make it a little bit more readable, a little bit more reusable, and so forth from there. Okay. Okay, now I'm going to go into just doing some basic testing of this, and should validate anything before you go further, but I coded this quickly, but let's see what we can do. Now there was an example actual main that's provided with the start code, so example start, and this is just using our singly linked list and just using integers to do its work. We have the add to start of like 1, 2, 3, like we should see from the actual examples. Now one way to start validating this, we could write other tests and everything else, but at least we can do some visual inspections and start building up from there. Now provided with the code is that we can go through and maybe have a way to print out everything and seeing what's going on in the actual list itself. So we don't have that in this current class. So let's go write a very quick method that'll just go through printing the entire list out and the data to us. So kind of like a toString. I just want to do this separately here. So public void print list. And when this is called, it will just go through printing out the entire list to the console itself. And I'm just using this for testing purposes right now. So we need a reference, a moving reference to the start of the list. Let's type m equals start. Right here. I will then system.out. representing the arrows we have here. So start going to what's here. The very end, we'll just have it do the final printout, which should be the end of the list, which would be null anyways. Print ln, so it goes next line. And here we will just step through the entire list till we drop off the actual end. System.out.print. And I just want to print out the current data. I'm going to put in brackets to make sure it's easier to see. And we will just go m.getData, print out the actual data, print out an arrow saying what it's linking to afterwards, and then we will move our moving reference forwards. Right here. So this should print out our entire list. So let's go back to the very beginning of our singly linked list and see, here we go. Forgot that. Get this compiling. Everything's okay here. We can go to our add start and we can see what the list is doing now and see what we should expect. So we can print it out each time. So print list with just these free lists, just to test out our print and what we should expect to see. Now what I should see from right here is for this very first one, it should be start and then going to just being 1. This next one is, we should have start, it should be going to 2 and then 1, because this 1 was the beginning of the list then. This was the next list afterwards. And then here, start equals 3, 2, 1, because we're always adding to the very beginning of the list. Okay. This first one will make sure the list is empty, so it added beginning. This will be going to else and adding and moving, shifting everything around. So let's go and see how this went. Okay. So start goes 1 to null, start goes to 2 to 1 to null, start goes to 3 to 2 to 1. So far, it looks like our add to start method is looking nice. So we'll go to the top and try to go through each of these methods one by one. The is empty we're about. We've got the add to start. Let's now go down and do an add to end and see what happens. So first off, it would be nice to see what's going on here each time with the actual size. And I just noticed, hey, let's print out the size each time so we can see that we're validating how many times we went to the end and how many actual nodes we had. Let's go back to our print. And we will now update our start right here, and we will just add in printing out the actual size of the list each time. So I just want to see and make sure if that list size has been updated. Let's go back and run this. So list size is 1, list size is 2, list size is 3. Okay, we're good so far. Let's now go and do some add to ends right here. So instead of doing these list to starts, let's do some add to ends and see how it comes out. This time we should expect to see that goes to 1. Then it's going to 1 to 2. Then 1, 2, 3. So we can see so far start, size is 1, size is 2, size is 3. Start where it's end null, first element. Adding it to the end and adding the end. So far it looks like our add to end is working properly. Which is good so far. Dun dun dun. Okay. Here we have the add to end. Here we have the add at. So let's go through now trying to actually do some the error handling kind of stuff. So we'll go through not adding anything to the list. We'll not do anything with the list. We'll just see if those error statements were working properly. So if we went list.add at, we'll give it index even say -1 for negative. I'm trying to pass in a value 2 just to add to the list. This will not work for us right now because it's forcing us to have a try catch, because that's what that throw statement was doing. So catch the exception that was coming in right here. And we'll get the message that came with the actual exception itself. So now this should work. So we should be seeing when this runs that it's actually caught the exception and saying index out of bounds, so index out of range. So it's a -1, the exceptions came here, the add at didn't do any work, we came down here. Next is if we try picking any larger value, we're past the size list. So I'm going to go 0, see if that works as well. Okay, out of range, just like we want. There's nothing in the list yet because it's empty. And we'll even go a larger value. And index out of range. So we're good so far. Okay, next, let's add one thing into list. Add to start. We'll add just the number 1. So we should just have start arrow equals 1. Then we're going to do add at index 0. And so after this, we should have start equals right here 1, and start equals 2 with the way the add at will have to work. So remember we added here, so this is index 0, and so it's going to add a new node after this from right here, which will then add in that 2 for us. So I'm going to print this out each time, just so I can visually see what's happening. Okay, printing the list, we have the null. Okay, and this one here is adding to 0 and then adding to 1. So we found our first bug that we've got to go back and modify the actual code, because what we were expecting, the way that this method was supposed to work, for example, is that we should have gotten 1, 2, but this added it before. So we just have to go down if we're at index 0 with the add start, so there's something in here, and it probably has to do with the way that we have add start that's replacing the start. And the way that we modified while we were coding this, that this was supposed to work, is that the add at will add the new node after the current index where we're adding it to. So we can't call add start anymore, because our add start right now will take this current node, that's in here, the start, and right here it says this node next and moves the start back 1 step, and the way the add at was supposed to work doesn't fit with that anymore. So we've got to modify this here now to properly deal with the cases that we actually have. So it's wherever the current start node is, and it's adding after the current one. So we know here if it's index 0, that's what the start is referencing. So this would make sure that we have more than 1 for right now. And then what we need to add in is that this is at the beginning and modifying every reference after that. If we look ahead for our code, we already know that this code will make a new node. We have this as if it is empty, so we're okay here. This one gets the node, and this code we have here checking if we're at the end of the list to add it in here, or if it's in between 2 nodes for the middle to add. So what we can actually do is we don't even need to worry about this checking index 0 anymore. We can take all of that out. Since we're adding after the current one, we don't have to worry about a special case for the start. So we've now discovered that that was creating a bug when we thought of before, trying to fix the code. So this comes back if it's here new node, if the list is empty. Okay, well we don't need this anymore because again our check index already checks if it's out of range or if it's empty. So we can get rid of this and shrink the code down a little bit more. We have our get node getting the index, which would be 0. It's fine. If the next node after this is null, so it's the end of the list, it'll add it into the end. Otherwise, it adds in between. So if it's the start node, this will auto make sure the start node references to the new node afterwards, and we should be okay. So good thing why we're going back to actually error check handle this. Let's go back to our start and what we expect, and now rerun this and see if we've got it working properly. We can see here that the first one worked, but we still have another bug because now when it came down here for the 0, this then threw another exception. We're saying that we're getting a null reference pointer. Our exceptions is catching that. So we've got something else to go and fix. So the only way that we would have had that coming back is something coming down here for getting the node. So we have the add to start is anything that we're dealing with these actual nodes. I would suspect that there's something wrong with our get node. So if we go to get node, we have our checking our index, and I think it's right here. Okay, so that probably is going too far because if the index was 0, we start at 0, and while it's less than or equal to 0, so it's going one step too far and going to null. So we start this at 0, while step is less than index, because we start here, m equals start, which would be index 0. Then if there's any more steps, we have to do that, then we can move it forward. So what was happening here is by going equals, it was going one too far. So we have a +1 or off by 1 error. So we need to fix that and making sure that, okay, if it's index 0 at start, it won't go into this for loop, it'll then return. And what happened before is when this was index 0, it was moving one too far for us. So now let's go back and check the main. Oh, good. We've got this, and this important part why we need to go error check and check everything and think of different possibilities of what could be happening. So we've got what we've expected here. Let's just to be careful even go and add just one more starting in the very beginning and then start checking adding in between. So let's go add 3, which we should expect right here. Now that would be 1 would still be here, 2 would be here, but now we'd have 3 in between because we're going index 0, adding the 3, and then this should be here. So this is testing as before of, first one would have been when it's empty. This would have been checking now if we're adding to the actual start and getting it properly, and where it would have been the end as well. And now this is checking in between two nodes that we've inserted 3 properly. Oh, and we got this one working. Our size is right, 1, 2, 3. We got 1, 2, 3 starting. Let's even go crazy and just do like another actual additional add. So let's add 4 in there, which we should get arrow. So 1, 4, 3, 2. So 4, so 1, 4, 3, 2. Okay, we're doing good so far with that. So we know we've got, after this is the list, so we can go on and start checking each of the other methods to make sure that they're working properly. So far it looks like we've got the add at. We've modified that we had errors within here. We discovered we had an error in our get node, so good, but we know get node's called other places. So we go to our get node, we fixed it here. Our get now we can start checking and validating if it works properly, and we can also properly use the size. So one way to check if the get is working is just go through getting each individual elements. We know we currently have this. We know we had that actual size, so let's just go for 1 by 1 getting each one. So we're just going through every index in the list, getting them one by one, and we'll just print stuff out. So I'm just printing out the index number, and then we'll get equal to what the actual data is. And we will just do our list.get, giving it the index. And what we should expect to see is we should see 4 things being printed out. So we get the number 1, then the 4, then 3. So 1 is at index 0, 4 is index 1, 3 is index 2, and 2 is at index 3. So 0, 1, 2, 3. So there we go. It's exactly as we expected. We've gone through each one, so it looks to me like the get method is working properly. Let's go back to our code. So we've got the get working. Next we need to check the find if it's working properly. We've got the size, so far looks like it's working right, and we've got our print. Okay, so let's check the remove. Let's go through different cases from right there. And what we can do is start, so I'm going to take out some of this previous code here. We'll still work with this list here that's like 1, 4, 3, and 2. I'm going to start removing where it's the start reference right here to make sure. So we're removing index 0. Make sure we got the right data back, and then we should have a list where it says 4, 3, 2 afterwards. So let's do system.out. We'll do the remove and just automatically print the data that it removes to us. So list.remove at index 0. So that should return back to us 1. And then we'll just print the list after this remove. So 1 should be printed to the screen, then we should see this proper list going out. Okay, good. So we got, oh, well, here's something slightly off with our code. Is that, okay, well, what were we expecting is that 1 should have been removed because we're doing it at index 0 from right here. But what we got was that 4 was returned, and we've got, boom, 1, 3, 2 going to null. So it means we've got another error, and we've got to come back here to our remove at indexes. We know that it was at the start from right here, but me looking quickly, looks like we had another error we left up here. This off by 1 for the indexes is that we're going starting at 0. We're going up from all the way here, but it was going 1 too far because we had this equal sign right here in the remove at. Okay, so because if I come down here, this still looks all right to me for the start. I think this was the same error from copying and pasting from that get method before updating stuff, and we remove that. So let's go back and see if we've got it working properly now. Okay, good. We do. We had 1 before, we got that data back, and then we've got 4, 3, 2. Okay, let's go back, and instead now, this is index 0, 1, 2, 3. Let's do a remove at the end of the list. So right here, which would be 2, so that's going to be index 3. So we should get the number 2 back, and we should see 1, 4, 3. There we got 2, we got 1, 4, 3. So that's perfect. Now let's do a remove that's in between. So this is index 0, this is index 1. So now if I go index 1 here, we should get 4 coming back, and then we should see 1, 3, 2. Good, we got 4 and we got 1, 3, 2. So it looks like our remove in between is working okay. Right now, let's try to just remove like a whole bunch of stuff from the actual list. So let's try removing everything and seeing what happens each time. So even if we're going to go down to even like completely emptying the list. So we removed index 1, we'll remove index 1 again, then remove index 1. So first it should remove the 4, then it's going to remove the 3, then it's going to remove the actual 2. So 4, 3, 2. We can see we've got the right list there, the 2 shrinking down, we've got the 1. Oh, but look, we got something going wrong here. Is that we got the 4 each time for these sizes, and that's not right. That size should be shrinking down. Let's go back here again, and we can see the removes. Oh, we did the list size removing from right here, but these other removes, we didn't do that. So that list size variable, again, if you're not careful, that's where it could be going wrong. So, okay, good. We're getting 3. We're getting down to 2. We got everything here. The sizes are going properly. Let's do one final remove and see if the list goes down to being completely empty. So removing the very last element, which should be at index 0. Oh, okay, good. We got the 1 return, list size is 0, list is null by that last case. So it looks like all of our work for the remove so far, the remove at is good, and we found just another small bug that we needed to deal with. Okay, one last thing to do. Let's go back, and we just need to check the find. Here we're going to need a comparator method now to do our work. To do that, the first thing is we need to make a comparator. And we're going to make one for comparing integers. We have to implement the comparator interface. Comparator. We specify the type right now. Right here. It's going to complain to us until we override the required methods. So that's our return right here. We're comparing two integers. We will assume that they're the same in the very beginning. So if we go if O1 is less than O2, result equals a negative number. So any negative number is fine here. Right here. So what I'm going to do is just save some space. Again, if O1 is less than O2, return -1. Else if O1 is greater than it's 1. And if we get down here finally where it hasn't gone the if or the else, then O1 has to equal O2. So result will be equal to 0 and return back. And remember, I'm getting those 3 values is by looking up the API and that definition of how the compare is supposed to actually work. So I have made this object here. I've made sure to save it this time. Then in the main, I can make this object for use later on. Our int compare, CMP equals now I can go and do the actual find. So I can go through and do a check to see what it should find or shouldn't find. So system.out.print. We'll just have it print out what it finds. So we'll do a first one where we do the list.find right here. and we are going to give it a number that's not in the list. So we know we have the numbers 1, 4, 3, and 2. So let's just put the number 5. It's not in that list. We're passing in a comparator, and so this should return back to us null, saying that it hasn't found the actual object. So we got this from here, and something looks like it's going wrong so far in our find now as well. So we got to be careful from here that this was 2, 4, 3, 2, and this returned back 1. So that doesn't seem right. So we need to go back and look at our singly linked list and go back to our find and see what's happening in here. Okay, we got m equals start for the actual list, while m doesn't equal null. It keeps moving through everything else. If m is equal to null, and oh my god, I can't believe the error in this one. Can you guys see it? Can you see it quickly if we look to this? It went through. We had m equals to start. We have, while m doesn't equal null right here. We have getting the data out of here. We have this comparison here. We never actually move it forwards. We never actually go m equals get. It's like not having a plus plus in your for loop. We never actually moved it forwards at all. So let's go see what happened here. Maybe it goes through slowly. If we equals a start, okay, it won't be equal to null if it's got the data in the very beginning. It's going to get the data out. It's going to do the comparison between the two of these, which is going to go into our int compare. It's going to say again, we have a result equals 0. Oh, and I can see another bug that I introduced by going too long and recording these videos late at night. So in our int compare, I had changed the result variable and I wasn't setting it here. So multiple errors that are just coming back to plague us. So one was in our find method, is this m equals get next. And next was in our int compare, we didn't actually return the result. Okay, let's see now if it's working properly. Okay, we're good. This time it worked properly. We got null. I go back, so that's data we're in here. Go for looking for the -1 as a value. Should also not find it from right here. And then next we could have, let's look for 3, so a value that's in the actual list. So it did return 3 to us, and let's just do a few ones. I like to do in the beginning, so we should get 1 back if it's the start node. Okay, we got that. And then 1 if we look for 2, which would be the very last node in the list. Making sure, because we've gotten one that's in between, we've got one here. Now let's see if we can make sure that it works right at the very end. Okay, yep. So far that's looking good. So I think so far based on these tests, maybe there's other bugs, but these quick tests we've done, we've got stuff for our singly linked list working in this case. So again, a lot of the bugs were my own bugs. I didn't purposefully introduce those, but it's why I wanted to test this before going on, is that I went through this, but even I can make mistakes no matter what I'm doing here and coding these quickly while talking at the same time. So I went through and had to do some testing to validate that everything worked before moving on to the next step and trying to think of what are different cases, a way that I could test the actual program. So at this point in time, I'll stop here and you should go back and review looking at the code. I will open up the singly linked list here and I will just go through it slowly from the top, so you can pause the video if you want each time I'm in here if you're trying to copy the code down. So even popping it from the top. We have our isEmpty and add to start methods. So pause now if you want to copy those. You have add to end. You have the add at method. Get node. Our get on the index just to get the data. remove at. Then your find. The size, check index, and then finally print list. So again, try to go slow there, so if you want to go back and pause the videos and type out this code and test everything yourself. Other than that, we'll keep moving forwards with linked lists and practicing, because the next thing is dealing with how would you do this with a doubly linked list? How would you deal with other special cases and drawing stuff out? I'm going to stop now. It's been a long enough video, but I hope all of you are doing well, and that as I end every video, maybe just continue being the awesome people you are, and remembering that if you can take care of yourself, then maybe you'll be better off to be able to help take care of other people. And even if it's a small thing in this world, maybe it can just help to make someone else smile or make someone else's day a little bit better instead of making it shittier. So, continue on.